A parent theorized that his daughter spent more time on her cell phone than his son. He randomly selected 27 calls made by his son and 25 calls made by his daughter from his past phone records. His son's calls had an average length of 23.5 minutes with a variance of 28 minutes. His daughter's calls had an average length of 36.1 minutes with a variance of 35 minutes. Find the 99% confidence interval for the true mean difference between the length of calls made by his son and his daughter. So right here it says find the confidence interval. So we have to find the 99% confidence interval for the true mean difference. So true mean difference. Okay, so at least we know what technique we're supposed to use in the problem. That key phrase gives us that. The other thing we want to look at here is this line here. It says do not assume equal variances. And we notice that the sample sizes are small, but they don't want us to assume equal variances. So at this point, when we have that scenario, we have to approximate the t-distribution, and we have to use a very special formula for the degrees of freedom, which we've used in a previous problem. Okay, so then finally they ask us, is there a significant difference between the length of time spent on the phone by his son and his daughter? So let's work out the confidence interval and we'll answer that last question. So initially what we want to do is record all the information from the problem. Let's write that down in a neat, orderly fashion. So let's start out with the sample sizes. And let's begin by putting the son first and then the daughter second. Okay, so for the son, the sample size is 27, right? 27 calls made by his son, 25 calls made by the daughter. Then it says that his son's calls had an average length of 23.5, right, minutes with a variance of 28. That's interesting. They give us the variance here as opposed to the standard deviation. So S squared is what we're given, and that variance was 28 minutes even. Okay, now his daughter's calls had an average of 36.1 minutes with a variance of 35 minutes. Okay. This is find the 99% confidence interval. So the confidence level is 0.99. Alpha, therefore, is 0.01. Okay, so from there, let's go ahead and do our second step, which is to get our table value. Now, because the sample sizes are small, we're going to use T alpha divided by 2 as opposed to Z alpha divided by 2, right? So the alpha divided by 2 is easy enough. That's 0.01 divided by 2. That's going to be 0.005. So we'll use that, look that up on our t-table. However, the degrees of freedom are complicated in this scenario because we're told that we cannot assume equal variances. And the sample sizes are not equal. So because of that, we're going to use this Well-Sajolate approximation method. So we have this formula here, or this set of techniques that I've written down. And basically, when assuming unequal variances, we use this for the degrees of freedom. We have to calculate this complicated fraction, and then when we're done, we'll truncate the answer and use that as our degrees of freedom and go to our table and look it up. Okay, so let's calculate that for this problem. So first thing we want to do is end up with A and B. So let's calculate A and B. Now, A in this case is the variance divided by the sample size. We have the variance, so A is just going to be 28 over 27. And B will be its variance, 35, divided by the sample size, 25. All right, so let's see what those give us in our calculators to get those as decimals. So 28 divided by 27. When we do that, we get this number 1.03 ... right? All right, so I'm going to write that down and I'll store it in my calculator. So 1.037 ... and I'm going to store that in my calculator under A, so I have it there for later. Okay, let's look at the next one. It's 35 divided by 25. And when I do that, I get 1.4. And again, I'll store that in my calculator for B. Okay, so now I have my A and B stored in my calculator. Let's fill in that complicated fraction then. Okay, so the fraction is going to be A plus B squared, so it'll be 1.037 ... plus 1.4 quantity squared, all divided by this pair of fractions. So A squared, 1.037 ... squared, divided by its sample size of 27, sample size is minus 1, so 26. And then add that to B squared. The B squared in this case is going to be 1.4 squared divided by 1 minus its sample size, so in other words, 24. All right, let's take that now and plug it into our calculator and work out that entire fraction. So I have it stored in A and B, so I'm just going to put A plus B quantity squared. If you don't have it stored, just use the decimals, right? Make sure you put the entire denominator in parentheses so you don't make a mistake here. So again, you would type in 1.037 dot dot dot. I'm just going to do A squared divided by 26 plus B squared divided by 24. Close it up and hit enter. And when you're done, you get the answer 48.27, so on and so forth. We actually don't care about what the decimal point is because we're just going to drop that and say the answer is 48, right? We have to truncate it, so we're going to tear off the decimal point and ignore it, and just use the whole number part of it. Okay, so 48 is our degrees of freedom finally, so we'll go to our table now, and we will look up under 48 degrees of freedom, alpha 0.005 in one tail, and when we do that, we should get our t-table value for the problem. All right, so let's go to the table and look that up. Okay, so we're looking up 0.005 in one tail with 48 degrees of freedom. Okay, so the answer is somewhere between 45 and 50. Again, we'll take the larger value between those two, though. So since our degrees of freedom is between these two numbers, we'll take the larger critical value. So that's going to be 2.69. Okay, so we have our t-value as 2.69 from our table. And now at this point, we want to go ahead and calculate our margin of error. Okay, so the margin of error formula, remember, is t alpha divided by 2 times the square root of the variance for the first population over its sample size plus the variance for the second population over its sample size. So remember, these are the variances, and we were given the variances in our problem, so we don't have to do anything other than just plug them in. We don't have to square them, in other words. So 2.69 times the square root of, in this case would be 28 over 27 plus 35 over, 35, forgive me, 35 over 25. So 35 over 25. Okay, plug that in, let's see what we get. So we'll have 2.69 times the square root of 28 divided by 27 plus 35 divided by 25. All right, once that's all in there, go ahead and close it up, hit enter, and we'll finally end up with the answer 4.1993 dot dot dot. So I'd like you to store that so you don't round until the very end, or just write down enough decimal places so you don't commit any extra error until the end, right? All right, now from there, once we have that, we're going to plug that into our formula x bar 1 minus x bar 2 minus the error. And then same thing on the other side, x bar 1 minus x bar 2, but we're going to add the error. Okay, so once we have that, we'll be able to finish our confidence interval and have our solution to the problem. All right, so let's go ahead and do that then. I'm going to subtract our sample means, so we'll say 23.5, that's the son's time minus the average time for the daughter, 36.1. And when I do that, I get negative 12.6. So negative 12.6 minus the error, and negative 12.6 plus our error. All right, let's see what that turns out to be ultimately. So minus 12.6 minus the error gives us negative 16.8. So negative 16.8. And then we'll do it again, but this time adding the error in. And we get negative 8.4, negative 8.4. Okay, so in this case, what we see here is that this interval is fully negative. Remember, if the interval is entirely negative, it means that the second population or the second sample set of data was statistically larger than the first sample set. So in other words, we can say that we're saying that we believe that it's a statistically significant difference between the daughter's time on the phone and the son's time on the phone. And because the interval is negative, it means the daughter, the second one in our subtraction, had a higher value than the son's, which means that this number, the sample mean, is bigger than the son's mean, and it's significantly bigger. So in other words, even after subtracting and adding the margin of error, we still get an interval that's negative on both sides, which means that in the worst case scenario, the daughter spent 8 minutes longer on the phone or so than the son, and in the other scenario, or the best case scenario, she spent almost 17 minutes longer on the phone than the son. So it looks like the daughter does indeed spend more time on average on the phone than the son. Okay, so that's our solution to the problem. And when we come down here to answer this last part of the problem here, is there a significant difference? The answer for us is yes, there is a significant